Yeah, thank you so much for the invitation and the introduction. I'm really excited to talk about the work we've been doing. It's going to be a combination kind of the work that I did with Johannes Lurker and Charlie Campbell in my postdoc, and then roughly maybe 50-50 over the past 5-6 years between my time there and then also my time at U of M. So just to give you kind of a setup of what I'll be talking about, I'm really of the opinion that chemical engineering, and in particular, the field of surface catalysis and catalysis in chemical engineering and chemistry is going to play a major role in enabling renewable energy technologies. So I'm going to talk a little bit about, just because everybody as a reminder, I'm sure a lot of you are aware that electricity and transportation energy currently are provided by fossil fuels. And so when we're talking about renewable energy technologies, we're talking about kind of converting away from fossil fuels to other species. And I believe that particularly electrocatalytically produced fuels are going to help the transition that's necessary to kind of a sustainable energy production model for the world. And I'll talk a little bit about that, and I'm happy to discuss more at the end if you have more questions. But just to give kind of a concept of where we're coming from. But specifically the science that we're going to be talking about, which will kind of be the majority of it, is how we can incorporate solvent effects. I mean, this particular solvent effects that we'll be talking about is the aqueous phase, but we think that really it can allow us to transfer a lot of the intuition that, over many, many years, people have gained from doing gas phase catalysis measurements. Really, we're trying to take that type of model of the fundamental heterogeneous gas phase catalysis and show that it can be transferred to condensed phase catalysis, but you have to incorporate these solvent effects to kind of get things to work like that. And then the last part of my talk, and I'll probably take a break just to take questions after we kind of go through that. The last part, I wanted to talk about why it's so important to understand how adsorption is occurring, how the coverages are influencing the reaction rates, and more importantly, how we can use the electrolyte or the condensed phase, this solvent phase. We can actually use that to control and increase rates for hydrogenation reactions that I think are very important for moving forward in sustainable energy production. So I'll start off with acknowledgments, just to kind of give, maybe a portion of this talk was really the work I did at University of Washington with Charlie Campbell. It was a joint postdoc between Charlie Campbell and Johannes Lurker. So we had a lot of staff scientists that I worked with. The X-ray absorption measurements we did were all done at Oregon National Lab. Mali Balasubramanian was the beamline scientist there, and John Fulton is an excellent staff scientist that really helped me build some of the cells we used to do that. And then there's theory people that we collaborated with there, and I was funded by these groups. So this is my group at University of Michigan. So I know it looks a little scary now because we're all very close, but this was actually Thanksgiving 2019. And to prove that, actually my newest student who I'm co-advising with Soyo Linnick, who's also at Michigan, is not in the picture. It's not because we didn't invite her, it's because it was so long ago when we were actually allowed to do, have groups like this where we could be close without masks. But the particular students that have been working on the hydrogenation work that I'll talk about today are James Akinola. This is a picture of him. And then it's in collaboration with Professor Brian Goldsmith, who does the computational work that I'll be, majority of the computational work that I'll be talking about is with his student Isaiah Barth. And that work is all funded by the NSF through their electrochemical systems program in CVET. So when we're thinking about just kind of the world, right, and what is happening in the space of energy, we know that energy demand is increasing, right? So the demand for power, the demand for energy is going up and up with time, right? To the point where I think it's about 18 terawatts is roughly the power demand in the world. And if we look at where this is coming from, 80% of total energy and about 66% of electricity and an even higher fraction of transportation is coming from fossil fuels. So the fact that the energy demand is going up by itself is not necessarily bad because a lot of it is going towards improving lives, right? It's going towards powering jet fuels for transportation, of course, not nearly as much right now. But, of course, we're getting electricity to power the laptops, right? That's kind of what's replaced me taking a flight to go give a talk now. And then, of course, in Michigan, especially now, energy is going towards, heating, which is particularly important, right, for us in cold places like Michigan. So the idea that, you know, we have a greater demand for energy because there's a larger population inherently is not a downside to it. It's just that the mode in which we're getting this energy currently has some side effects. So I'll talk a little bit about where this energy is coming from using actually a picture from the place where I did my PhD, which was UC Santa Barbara. And these are the oil rigs off the coast of the beach near UCSB. And basically what they're doing is they're pulling out fossil fuels, you know, that are being non-renewable fossil fuels that are being used for combustion to power all of these things. So we can look at just kind of a quick calculation of really what's happening with this, right? Over roughly the past 100 million years, there's been 3 trillion barrels of oil that have come from, you know, solar energy coming to Earth, forming plants. Those are, you know, decomposing, dying, and slowly over hundreds of millions of years, converting into oil. So if we think about this process, right, in this 3 trillion barrels of oil, there's about 500 terawatt times years. So that's the amount of energy in that. They were formed over 100 million years. So we can see that this is really a kind of tiny production rate of these fossil fuels, right? So of course they are, you know, ultimately they're coming from the sun, but over such large time scales that they're not being renewed, right? It's extremely slowly. The only reason we have so much of them is because it's been so much time for the sun to send energy to the Earth. And when we look at the current power use for transportation, you know, I'll be focusing a little bit on transportation because I think those liquid hydrocarbons are really fantastic for doing transportation. You can see that we're consuming about 5 terawatts, which means that why we call these non-renewable fossil fuels is because every minute the world uses the amount of energy that it took nature 2 years to store, right? So if we're continuously using these fossil fuels, they're just going to be used up. There's no kind of way around it, right? And probably even before they're used up, they'll become too costly to continue using. So that's kind of an argument just on scarcity, an argument on cost. But I think even more compelling argument is that by combusting these fossil fuels, they're going to be emitting CO2, right? And this is evident by, if we look at the parts per million of CO2 in the atmosphere, it's just going up and up as more and more of these fossil fuels are combusted. And the effect of putting CO2 in the atmosphere, there will be some impact on the environment. I believe, and a lot of scientists believe, that this will be a very negative impact. People are working to quantify how bad this impact will be. And I won't really focus on that and talk, but I'll just kind of say what you know, NASA has done, and a lot of climate change scientists believe, is that this increase in the amount of CO2 will lead to more frequent wildfires, longer periods of drought, increases in intensity and the number of tropical storms. So really, we want to shift away from having so much of our energy be fossil fuels, meaning, you know, fuels that are in the ground and then have a net emission of CO2 when they're combusted, and shift more to power by renewable energy. So when we look at that, and if we try to think about the projections and trying to convert from a large fraction of fossil fuels to a higher fraction of renewables in order to combat CO2 emissions, one of the disadvantages of this is that as this increases, the percentage of the renewable share increases, which is predicted to be around 50% by 2050. We can see that we might have this issue where there'll be this supply, which is, you know, something like a wind turbine or a solar panel. It really just gives electricity or gives energy when the sun is shining or when the wind is blowing. And this might not necessarily match the demand. So there might be a peak in demand during the middle of the day. Maybe that's not when the wind is blowing. So there'll be some need to how can we store this electricity, right? And then use it when we get this energy back. So really, overall in my group, this is kind of a study that we've been doing. And really, we think that electrocatalysis and electrochemistry is going to play a major role in being able to take this new renewable, specifically renewable electricity that's going to be more abundantly available and using it to give people energy on demand. So the couple of projects that we're doing in the group, I'll just mention briefly, is we're working a lot on just direct energy storage using redox flow batteries. We're also looking at trying to do electrocatalytic waste remediation, so trying to take things like nitrate that are polluting a lot of groundwater, especially in parts of the United States, but also all over the world, and thinking about how catalysis can allow us to convert these molecules in very controlled ways, along these heterogeneous surfaces, understanding the transition states for these, and eventually producing useful things like ammonia and things like this. So these two projects I'm really not going to talk about today, but I'm very happy to talk about them after if you have any questions, and I can also, even offline, I'm happy to talk about them. But the specific thing that I think is particularly relevant to producing transportation fuels and is especially relevant to CO2-free energy, or CO2, at least CO2 neutral energy, is thinking about how we can make fuels and chemicals using new dispersed or underutilized carbon resources. So these might be things like waste biomass or different products. Even directly, you might do it from CO2 potentially. But we want to think about, we'll have this abundance of renewable electricity in the future. How can we combine these two new feedstocks that have historically not really been used by chemical engineers and chemists, studying catalysis? And how can we combine them into low temperature processing, kind of made more necessary by doing types of manufacturing, chemical manufacturing in very distributed scales. And really, when we're doing distributed kind of smaller scale things, electrochemistry, which scales kind of with an area basis rather than a volume basis that you might be familiar with from large gas phase reactors, really electrochemistry scales down to these distributed systems very, very well. So just as a reminder for anybody it's not super familiar with electrochemistry, basically what we're going to do is take this renewable electricity, we're going to have an anode, so an oxidation reaction, a cathode, so we're doing a reduction reaction, and we're going to try to utilize some of these carbon resources to eventually make useful chemicals and fuels that can go into jet planes, that can go into useful chemicals for manufacture, that can go into powering things like diesel and all those types of things. So this is a very broad picture, right, of, we take some type of carbon resource that's not a fossil fuel. We're going to use renewable electricity. We're going to use that to manufacture things. And then we're eventually going to be providing the things that historically have come in from fossil fuels. We want them to no longer require fossil fuels for that. But this is kind of a broad picture, and I'd really like to focus in on specifically the cathode of an electrochemical reaction. And I'm really going to focus on the cathode for the electrocatalytic hydrogenation of a bio-oil model compound. And the main one we're going to do is study how phenol, so phenol in an aqueous or acidic stream, how it's converted on platinum group metals to things like cyclohexanone and cyclohexanol, right? And then the other part of this talk that I'll be focusing on, which kind of came out of the result of trying to understand this reaction, is what is the effect of water, right, the solvent phase water, when we're trying to do adsorption of some organic, especially large organic molecules on metal surfaces. How is it different from the gas phase? So those are the two real things that I'll focus in on for the science of this talk. So to give you a sense of what we're talking about when I mention bio-oil, in case you're unfamiliar, basically the idea is we have this waste biomass or waste organic or oxygenated hydrocarbon species. Typically what will happen is if you're trying to convert them ultimately to some fuel source is you'll first do a pyrolysis step. So you'll heat them up at really high temperatures. All the lignin in these compounds will break down into species like phenolics, basically. So phenol is like the simplest form of the phenolic, but there's a lot of these types of compounds that are present in bio-oil, and they're very soluble in water, so you'll have a high concentration of those. So bio-oil by itself is not a good fuel. It's corrosive in engines because of some of the acidity there. There's tons of water around because it's still pretty soluble in water. And then also, just because you can see there's all these unsaturated bonds, it's not very energy dense. So it doesn't have these extremely nice properties that we get from fossil fuels when we're doing transportation. So in addition, it's also just kind of unstable. If you try to treat it and do things like that, it forms polymers, it clogs up reactors. It's really, really terrible stuff. So the specific reaction that we've been focusing on at PNNL and then also at the U of M is how can we increase this hydrogen content and then also make this CO cleavage more easily? And how can we potentially power it by renewable electricity? And how we've been focusing on that is we're thinking, how can we do electrocatalytic hydrogenation? So this is basically doing these hydrogenation reactions they're reduction reactions, so they're involving electrons, so they're at the cathode of this overall system. Taking phenol, going to cyclohexanone, then going to cyclohexanol, and eventually we'd want to go to something like cyclohexane, where they could be, very similar to compounds such as jet fuels. But really, what I'll be focusing on is the hydrogenation portion of this, and then there'd be a deoxygenation step that's typically done with the use of something like a zeolite or an acid catalyst, which Johannes Lercher does a tremendous amount of work for, but I won't be focusing on in this talk. So really, the question is, okay, can we do these reactions, right? We want to do them at low temperature for these distributed systems. And can we do them at rates that are reasonable to kind of make these conversions and actually be able to make products, right, that we can use at the necessary time scale? So for those of you that are, I'm sure a lot of you are very, very familiar with hydrogenation reactions in general, especially, so we'll start from gas phase type reactions. So most heterogeneous catalytic reactions, they'll involve some type of adsorption, right? So we're absorbing the hydrogen, we get some coverage of hydrogen on the surface. We absorb the species A that's being hydrogenated. Then there'll be a surface reaction where the hydrogen will add to the phenol. The rate of that specific reaction will have some rate constant, and then it'll be the coverage of hydrogen multiplied by the coverage of phenol, right? So you need to have phenol or whatever your species is on the surface. You need to have hydrogen on the surface. They react together, and that rate tells you, how fast you're forming your product. And eventually, you'll have to desorb these species. So that's just a reminder for kind of what's a Langmuir-Hinchelwood type surface reaction here. And if the overall rate is dominated by the step 2, the rate determining step, basically assume that adsorption and desorption are so fast that they're equilibrated, and we can estimate the rate by this rate law. So what is controlling these coverages in that case is basically what's the equilibrium constant of the adsorption and desorption reactions, right? So this equilibrium constant KEQ basically is related to how strongly that species adsorbs. So the delta G of adsorption. Basically what this means is you have a big equilibrium constant if you adsorb a species very, very strongly. And then if you adsorb a species very strongly, its coverage will be very high, as we're saying. So let's say something like phenol adsorbs very strongly. It'll have a big equilibrium constant. The surface will be covered in phenol, is roughly what this is telling us. There's this extra term here that sometimes we need to use, where this alpha term is basically you'll see features like that is if the adsorption energy is a function of the coverage, we might need to incorporate that. Meaning that if phenol adsorbs very strongly at low coverages, but very weakly at high coverages, we need to incorporate that into the mathematical model. So this is kind of the concept for understanding how a surface reaction in conventional catalysis is really, really dictated, or the reaction rates are dictated by the coverages, which are dictated by equilibrium constants, and those are related to adsorption. So this is just, in gas-phase catalysis, very well known. The adsorption energies of your species that are reacting are really, really important for understanding kinetics, right? The other way this is incorporate the adsorption energies can kind of come in is that your rate constant here is typically defined by something like an Arrhenius equation. And then these activation energies associated with that are often defined by what are called BP Bronsted-Evans-Polanyi relations, where the thermodynamics of the reaction also gives you an approximation of the kinetics. So what we're quite interested in here, and our hypothesis is that the adsorption energies, right, this delta G of adsorption of these molecules, for aqueous phase, for electrocatalysis, we really, really think if we understand those, it'll give us some insights into the kinetics of these reactions. And this can be summed up by basically saying we hypothesize that this concept called the Sabote Principle, it's going to exist for the aqueous electrocatalytic hydrogenation, but thermal catalytic hydrogenation, which is just rather than doing it electrochemically, you do it directly with hydrogen. We think that this is going to exist on platinum group metals. What the Sabote Principle basically says is that if we have a phenol group and we have these protons or hydrogen, we don't want the phenol to adsorb so strongly, so very downhill, and the hydrogen to just adsorb so strongly that we can't react it away. We don't want them binding so weakly so they can't even get onto the surface to react in the first place. but we want them to bind kind of just right. So this is the Sabote principle, is basically saying there be some delta G adsorption or delta H enthalpy or free energy, depending on what you're talking about, that'll be optimal in order to carry out this catalysis here, right? So this will allow us to have low barriers for adsorption, for reaction, and for desorption. And there'll be some optimum adsorption energy of the phenol molecule of the hydrogen onto whatever the catalyst surface is in order for us to convert this. So, right, this is very well known in gas phase. There are actually already a lot of electrochemical reactions where this is obeyed, but we wanted to see if this is kind of also obeyed for these large organic molecules doing aqueous hydrogenation. So, starting off, as kind of a background. So Spencer Carey, who is a student who recently graduated from Charlie Campbell Group, and this is not my work. I'm just, but this was work done by Charlie Campbell's group that I wasn't a part of, but I'm going to be talking about a little bit. What they did is they looked in the gas phase, so in ultra high vacuum, they looked at the heat of adsorption, right? So negative of the delta H of adsorption. That's why the numbers are positive. Of phenol on a couple different surfaces, right? So the relevant one is the one in red, where they looked at phenol adsorption on platinum, and what they saw is that the phenol is adsorbing, I think you can see me, flat, so horizontal with the aromatic ring onto the platinum surface, and with very, very strong energy. So the phenol in the gas phase is absorbing extremely strongly on platinum 111. Eventually, these energies here, these heats are when it's absorbing multi-layers, so these are not really the relative energies, but we're talking about the energy here where phenol is absorbing extremely strongly, approximately with in UHV with a delta H of adsorption of negative 200 kilojoules per mole. So just a reminder, the reason it's negative here and positive here in the graph is because in the graph it's heats of adsorption, so how much heat is released, whereas here this negative is corresponding to it's a very favorable adsorption. So when you look at DFT calculations that incorporate the effect of van der Waals, or that incorporate van der Waals effects, you can see that they get these numbers very, very accurately. You can see that on platinum, you absorb phenol with negative 215 kilojoules per mole, very close to the numbers that they see in ultra high vacuum, where there's no solvent, of course. And then rhodium, another platinum group metal, absorbs phenol even stronger, negative 269 kilojoules per mole. And you see that there's this delta here of 54 kilojoules per mole. So both of these surfaces, platinum 111, rhodium 111, absorb phenol very, very strongly. My collaborator, Brian Goldsmith, has recently done some calculations, very similar numbers. They both absorb extremely strongly, rhodium even more so than platinum. You'd expect these things are not going to react at room temperature. Phenol just absorbs too strongly to react, to be hydrogenated on platinum or rhodium. This is exactly what you see in the gas phase literature. Whenever you're trying to look at, can phenol be converted on platinum, rhodium, palladium? All of the measurements are very high temperatures, which is basically getting to high enough temperature where you can desorb these species, right? So 250, 300 degrees Celsius, that's kind of what in the gas phase literature, people are seeing for these kind of conversions. But interestingly, at room temperature, right? So, 23 degrees Celsius, 298 Kelvin, in the literature, and also, our groups at PNNL have seen, and of course, we've reproduced that in Michigan as well. We can see that platinum on carbon and rhodium on carbon can convert phenol very easily in the aqueous phase. We get moderately high turnover frequencies. So these are the moles of phenol converted per second per atom of surface, either platinum or rhodium. You can see that by applying a negative potential, we can convert these species. Phenol is being hydrogenated in the aqueous phase on both of these. Interestingly, platinum on carbon and rhodium on carbon have extremely similar turnover frequencies, within maybe a factor of 2 or so, basically the same activity. So there's two surprising things with this, is that one, platinum 111, we know that phenol binds 200 kilojoules per mole. So really, why is it able to react? It binds so strongly. How is it even reacting at room temperature? And the other surprising thing is that rhodium 111 binds even stronger, right? So it's even stronger. It's not 200, it's 250 kilojoules per mole. Why you know, everything, our intuition from the gas phase catalysis is these are so different adsorption energies. Really, these rates should not be the same. What's going on? Okay. So we thought first, well, maybe it's something special about electrocatalysis, but we did a lot of investigation. Just rather than putting the hydrogen on electrocatalytically to form these hydrogen groups on the platinum, then the phenol comes down, absorbs, they react together. We just directly added hydrogen. And really, there didn't seem to be a major difference in this rate determining step. So it's basically what's controlling the rates of these reactions is, again, like I said, these surface hydrogenation steps. So you either provide the proton electrochemically to make a hydrogen, or you provide hydrogen in the thermal case, like H2, gas phase hydrogen goes into solution, dissociates on the surface, and now you have a hydrogen here, then it hydrogenates, but the barriers are the same, product distribution is the same. So it doesn't seem like it's something inherently, oh, electrocatalytic is undergoing a wildly different mechanism. It seems like it's still a kind of a surface reaction occurring here. Phenol is absorbing on the surface, it's reacting with hydrogen, and somehow it's able to convert, is what we're kind of seeing, which is a little bit strange. So we did a little bit more study with this, where we looked at the turnover frequency. We changed the phenol concentration over a little over 2 orders of magnitude here. And we saw that if we look at the turnover frequency, we can see that at very, very high concentrations of phenol, as we would expect, the surface is completely covered in phenol. There's not enough hydrogen on the surface to react, and the turnover frequency goes down. Likewise, if there's very low phenol concentration, the surface is completely covered in hydrogen, right? We're keeping a constant pressure of 1 bar hydrogen. This is a thermal measurement here, but we see very similar stuff if you do it electrocatalytically. And then what we can do is we can actually fit, this line here is actually a fit using our Langmuir Hinshelwood model here, where we say the rate is equal to some rate constant that we're fitting times the coverage of the hydrogen times the coverage of the phenol. And remember that these coverages are basically defined by how strongly hydrogen is absorbing to the surface. So KH is the adsorption coefficient for hydrogen, and then how strongly the phenol is absorbing to the surface, which is given by this K phenol of 33 here, right? Which is actually quite a small K phenol. So we see that, well, it seems to be that if by looking at the rates, it is obeying a surface hydrogenation model, right? You put phenol on the surface, you put hydrogen on the surface, they're competing for sites, you know, and then if you have too much of phenol or too much of hydrogen, your rate goes down. You need it to be kind of at the sweet spot where you have the right concentration of phenol, so you're not completely poisoning your surface. So everything is kind of consistent from a kinetic standpoint with what we know very well from gas phase surface hydrogenation reactions. It's just somewhat confusing. Why are these adsorption constants so different than what we see in the gas phase, and that we, you know, especially DFT people are calculating in the gas phase. It's very confusing because you know, they'd initially just predict, yeah, this is not going to be reactive, and then we kind of would have missed out if it wasn't for looking at the literature and saying, well, it has actually reacted in the aqueous phase. So what we decided to do a little bit first is just think, okay, maybe we're making the classic blunder in catalysis where we assume we have a surface, but under reaction conditions, it's actually completely different. So we built a cell to do in situ X-ray absorption spectroscopy. So basically, this is the cell here where we can flow electrolyte in. We develop a little electrochemical reactor where we can control the potential. We have a carbon felt material here that we put our platinum and carbon into this little bed here, and we make kind of like a little packed bed reactor for electrochemistry. We can control the potential, and then we can pass an X-ray beam through the catalyst while it's doing the reaction. So this allows us to be sure, do we actually have platinum here? Can we actually see kind of hydrogen and phenol on the surface? So we brought this to Argonne National Lab. We passed this X-ray beam through while we're converting phenol on platinum. And what we can see is that as kind of expected, if you have platinum nanoparticles, as you kind of start off, the platinum on carbon, as it's prepared, has like a surface oxide on it. But as soon as you start the reaction, you apply a negative potential, you can see that what happens here is this, this feature here for the black line is higher than this platinum foil. This is because of the oxide that's formed. As soon as we start the reaction, we are completely reducing the platinum surface. So we really do have a metallic platinum that's similar to what you have in ultra high vacuum. So it's not like we have some magical new surface. It is metallic platinum, and then the phenol and hydrogen are reacting on this, right? And we also see that there is a competitive adsorption. So what we do from this near edge information here is we can see that it's well known that if you have hydrogen adsorbed onto platinum, there's this feature here that when you take the difference between the species where there's hydrogen on and then the bare platinum, there'll be this little edge here. And then when we add phenol, that basically decreases. What that means is that phenol is displacing the hydrogen from the surface. So you no longer get the electronic interactions from hydrogen adsorbed onto the platinum that give this Zane's feature. We also did simulations, Niri Govind did simulations to kind of indicate that these are actually the features associated with platinum carbon groups on there. So it does seem like we have a metallic platinum. Phenol is adsorbing, it's displacing these species. You know, it's not that there's a brand new catalyst, you know, that's making it different from the gas phase. We did a little bit further work with the X-ray absorption, where we look at the fine structure, where we're basically actually able to see the scattering of the platinum and then both the carbon support, and then what we saw and kind of over several years kind of convinced ourselves is that when we add phenol, we're actually seeing the interactions from the scattering of the carbon atoms that are on the adsorbed phenol. So I'll give like a molecular, we also ran molecular, my collaborators ran molecular dynamics for this. Where basically what we're seeing is we're seeing the X-ray excitation of the L3 edge of this platinum is scattering off these carbons that are on the surface. And when we fitted all of this, we got the distance between this platinum and then this carbon from the phenol groups that are adsorbed onto the surface. And we see that that platinum phenol bond distance from X-axis, really it matches as if the phenol is absorbing very flat onto the surface. So that was our other concern. Maybe the phenol is not even absorbing the same way in the aqueous phase, you know, that's what's different, you know, but no, just like Charlie saw in the ultra-high vacuum measurements where the phenol is absorbing flat onto the phenol, the phenol is absorbing flat onto the platinum. That's really what we're seeing in our electrocatalytic measurements as well. So it's not like a completely different mode of absorption. It's still the same kind of flat absorption. So this really led us to the question, why is it that phenol is able to react in the aqueous phase on platinum and rhodium when in the gas phase it binds so strongly? And that really is going to bring the question of how do we kind of understand what is actually the adsorption energy in the aqueous phase? So the technique that we use for that is really is one that's very heavily used in the electrochemistry literature. It's called hydrogen under potential deposition. So this can be done on both platinum or rhodium, very fortunately for us. And basically what happens is you take protons from solution, you scan the voltage on like a platinum group metal. So this is just a platinum wire here. You're scanning the voltage down this way. Once you get to a point where it's favorable to adsorb, to reduce a proton with an electron and adsorb it onto an active site, you basically get a monolayer. So you're putting a monolayer of hydrogen onto the surface, right? Then if you scan the voltage back, it becomes unfavorable for that monolayer to form. It'll desorb. And because you're giving up an electron doing that, you get a current associated with that. That's why this current increases. And then we see all this hydrogen come off here. So fortunately for us, people have done a lot of really nice single crystal work where they're able to say that this particular peak is when hydrogen is desorbing from platinum 110. This peak is when it's absorbing from 100, so kind of step sites. And then this broad feature under this is when it's desorbing from platinum 111. So what's nice about this is that if you take the charge associated with this, you know that there's an electron for every open site here. So this basically, the charge from taking this current and knowing how long it took to do, how long it was passed, you can get a charge. You see that you can actually count the number of these surface sites that have had hydrogen adsorbed onto them. And even nicer, we know that we can actually kind of roughly deconvolute that there's a portion of this charge is from 111, like tera sites, a portion of it is from these step sites here. And then the sum of that is kind of what we were actually seeing here. So what we did is we looked at just the platinum in the complete absence of any phenol. We see this nice feature, but then we noticed if we add a little bit of phenol into the solution, what'll happen is that there's less of this hydrogen under potential deposition charge. Why there is less is because the phenol has now adsorbed onto the surface and is blocking sites from adsorbing hydrogen. So there's basically less open sites, right, for hydrogen to absorb. So we're indirectly counting here that when we think about this decrease or the fraction of HUPD that's inhibited by the presence of phenol, we can basically plot that with this point here. So there's a concentration of phenol and we have a point here. We go to higher concentrations of phenol and there's more and more blocking of sites. If you look at the shape of this, you can see that the peaks corresponding to the step sites go down first, right? Because the phenol is going to those sites first or at lower concentrations. But ultimately, basically everything is covered by phenol and we're not able to see any absorption of hydrogen anymore. So if we actually look at this, what we've kind of backed out from this is essentially an adsorption isotherm, right? So we've varied the concentration of phenol. We have something that's basically saying, okay, how many sites is phenol blocking? It's another way of saying the coverage of phenol, right? And we can actually fit those plots. And I've divided them up into two here, where the first, the one that's absorbing at lower concentrations is what we're gonna call S sites, right? These correspond to these facets here. And then at higher concentrations, they absorb onto the T sites here, where we're actually getting a weaker adsorption onto those species because it takes higher concentrations. So we can do the exact same thing on phenol or on rhodium. We can add higher concentration of phenol. We see more clearly there's these two sites. But the really interesting thing from this is then when we fit these numbers together, we can see that the adsorption of phenol on rhodium in aqueous phase was extremely, extremely similar to that on platinum, right? I'm just going to show those all together where we look at these energies. The energy for phenol absorbing on platinum and on rhodium really is almost the same. Despite, remember, there was this 50 kilojoules per mole difference in the gas phase energy. So this was quite surprising to us. So this was something that I'm going to explain in just a moment, but I also want to mention that now we have these delta Gs. So we know how strongly phenol adsorbs onto step sites, how strongly it absorbs onto these terrace, like 111 sites, and same for rhodium. We can compare this to, remember, we did it with the kinetics. We saw that we get, by fitting the kinetic data and using this Langmuir-Hinshelwood equation, we can get values for how strongly hydrogen is absorbing, how strongly the phenol is absorbing. And very interestingly, the absorption of phenol on this active site during electrocatalytic hydrogenation or thermocatalytic hydrogenation is extremely similar to how strongly the phenol is absorbing onto the weaker binding terrace sites here. So really what this is indicating is that there's two types of sites on platinum, polycrystalline platinum, that absorb phenol. There's a stronger binding site, and then there's this weaker binding 111 site. And the energy associated with the weaker binding site matches this kinetic. So basically it's indicating that the 111 or the terrace sites, those are the active sites, right? That's where the reaction's occurring. So they bind phenol really, really weakly in the aqueous phase, and they're what's dictating the reaction rate there. We see that based on thinking about that, we say, well, if we change the particle size, we can make bigger and bigger particles that'll have a higher fraction of 111 sites. So the turnover frequency normalized to the total rate is going to go up and up and up, right? And that's exactly what we see here. And we also saw that this occurs for rhodium. So we make bigger and bigger rhodium particles, bigger and bigger platinum particles, higher fractions of these terrace sites, more of these sites that bind phenol weaker, our turnover frequencies are going up. And with phenol, when we do hydrogenation of phenol, fit the data, we see a very similar behavior to what we saw for platinum. And again, these energies are, relatively very close for how strongly phenol is binding to rhodium 111 sites is kind of matching this description here, right? So we have phenol is reacting on these 111 sites. It's binding in aqueous phase extremely, extremely weakly compared to what we'd expect for gas phase. And in addition to that, so despite the phenol binding 50 kilojoules per mole stronger on rhodium than on platinum, they basically in the aqueous phase are binding the same kinetics. This, it makes sense that the kinetics would be the same because they absorb so similarly. But really, why is this? How is this possible? So what we did is this was work with Charlie. We looked at basically the measurement values that we had. So we have these from these isotherms from the cyclic voltammograms where we varied the potential and looked at the HUPD. we saw that we could get this delta G of adsorption of the species. We wanted to do a couple checks with this, so we just are going to convert them to measurements that you can do with solution calorimetry, right? So you can convert with Henry's law constant, you can get the organic from the aqueous to the gas phase. The reason we did this is that there's very well tabulated estimates of the entropy of adsorption of gas phase molecules. So this allows us to convert from a free energy to an enthalpy, right, by accounting for the entropy of adsorption. And then we can get the heat of solvation of the organic. And basically from this original isotherm measurement, we can get an estimate of how much heat should be released if this organic in the aqueous phase adsorbs onto a surface. So why we did this is because there are some tabulated values for a different molecule, granted benzaldehyde, solution calorimetry measurements for platinum, for rhodium. We get very, very good agreement between, how strongly, in this case, benzaldehyde adsorbs to platinum and rhodium between these methods. So basically why I'm telling you this is not just that our measurements are just not working at all. It really is that the adsorption in the aqueous phase is much, much weaker than in the gas phase. So just coming back to these numbers, if we do all this analysis, we're going to compare directly between the UHV calorimetry or between the DFT measurements. Even when counting for the entropy, all these types of things, when we're comparing these things, there's this huge difference in what we're saying. So platinum 111, our active site, rhodium 111, our active site, there's just some reason they're binding phenol much more weakly, even put on the same basis, accounting for all these things, than what we get from calculations or UHV calibration, right? So this question that I'm going to try to explain with the last little bit of the talk is, why is there this large difference in the observed gas phase versus aqueous phase adsorption? And then also the kind of the added thing is, how is it that there, at least there's this difference, there's this trend that we'd expect from the gas phase 200 to 60 kilojoules per mole difference. Why does that disappear when we go in the aqueous phase? So both of these things are going to be explained by basically kind of a simple bond additivity model that is going to account for these solvent effects. Specifically, we're talking about these flat molecular adsorption energies for something like phenol. So basically what we're doing is we're saying that normally in the gas phase, the molecule just goes onto the surface, adsorbs, but really in the aqueous phase, there's a lot more complicated things. We need to take the gas phase molecule, we need to solvate it is a portion of it. So just literally put it into solution, right? Then this metal, or like platinum 111 or rhodium 111, we need to displace a certain amount of water, right? So there's a footprint here, this theta, so this sigma term here, there's a footprint of water that's going to be displaced. We lose some energy associated with that, right? Essentially, this adhesion energy of the water or the solvent onto the surface, that's going to need to be moved up. We need to break the bond between the phenol species and the solvent, and then we need to kind of put that organic molecule down here. So this is all kind of detailed in this paper here, but roughly what it's saying is that the thing you don't have to account for in the gas phase is that the solvent is actually interacting with the metal surface to begin with. And in order to adsorb a large organic species like phenol, you need to move all of that solvent out of the way, right? Account for all these solvation effects, and then put the phenol down. So it's not necessarily that the phenol is not binding stronger to the metal surface. It's really that because there's solvent there already, there's an unfavorable displacement of the solvent, and that's what we're seeing in the adsorption isotherm. So really we're getting like an effective adsorption, right, of this value, like a 21 kilojoules per mole. We have to move so much water out that there's this really large penalty in displacing this water. So these numbers here are specifically phenol on platinum 111, and this number for the adhesion is measured as values that Charlie measured in the ultra high vacuum for how strongly water adsorbs onto platinum 111. But what we thought was especially interesting for this is now that we have this bond additivity model, we can actually look and see for platinum 111, we have gas phase adsorption, how strongly phenol adsorbs to platinum. We can actually, by knowing this displacement energy of the adhesion of water, we can do the same thing for rhodium, right? We have a calculation from, it's a relatively simple calculation Brian Goldsmith's group can do for this gas phase. And then we can look at, well, how strongly is the solvent, in this case water, adsorbing to rhodium? And if we assume this footprint is the same for rhodium and platinum, basically meaning there's a certain number of moles of water that's displaced for every mole of phenol that has to go down, we can see that we can at least find this difference is basically the difference in the platinum and the rhodium comes down to how different is their gas phase adsorption energy, but then also how different are they absorbing this solvent, right? And what we saw kind of roughly is we see in the experiments that rhodium and platinum in water absorb phenol about the same. They absorb in the gas phase about 50 kilojoules per mole different. But then because rhodium actually binds water stronger than platinum, basically this difference kind of disappears. Right? So I know I'm running a little out of time, so I'll just finish with this kind of last slide and then skip ahead a little bit. So using this bond additivity approach, what we were able to do is basically say, we start off with this gas phase energy where we say platinum binds phenol way too strongly to react. Rhodium binds even strongly, but then we see this aqueous phase, there's this huge difference. When we apply this bond additivity model, where basically all we're doing is we're saying that there's an enthalpic cost to having to move a certain number of water molecules away from the surface. And the enthalpic cost is larger for rhodium because it binds water stronger than platinum. It kind of roughly gives a good approximation for this. And when we incorporate this, it kind of starts making sense. This is why at room temperature, phenol can react on these two surfaces, right? Because it's not actually absorbing as strongly as possible, so it's not getting poisoned. So I know I'm going to skip the last few sections and just kind of go to the summary. I apologize for taking a little bit longer. Ultimately, what this has told us is that if we account for these solvent effects, it allows us to really determine these aqueous adsorption energies just using first principles DFT values. So you can calculate gas phase calculations. You get a good idea of how strongly the phenol is absorbing, how strongly these water molecules are absorbing using gas phase calculations. And then you do all the corresponding work to make sure you're accounting for solvation effects, just using tabulated values like Henry's law constant and those types of things. You can get very, very accurate numbers there. Since we know that hydrogen and phenol adsorption have a big role in the coverage and barriers for this, we can see that this really helps us identify what would be the active sites by knowing, okay, the species that's reacting absorbs phenol very weakly. This is the surface that absorbs phenol very weakly. And I apologize, I didn't get to get to it. But we're also able to use this by controlling the coverage of these species. By knowing the microkinetic model, we're able to increase the turnover frequency of these rates. And then the part that unfortunately I didn't get to, we're also, by modifying the binding energy specifically of hydrogen, by controlling the pH, we were able to get some accelerations there. So I'd like to stop and just give acknowledgments to all the people that have helped me so much with this work over the past 6 years. Sorry for kind of blowing through the time, but I'm happy to go through questions, any questions you might have. Thank you very much for listening.
Okay, thank you so much, Nirala. I mean, no worries about 4 minutes. That was really, really clear and really interesting. So I'll just have Nitish moderate the chat. Oh, and I guess, sorry, I guess I'll just do this one. Andy has a question.
Okay, thanks, Nirala. It was a really nice talk.
Thank you.
So I guess a question on the entropy part of it. So if I understood in the part, I guess you had this slide, we had sort of this flow diagram where you broke down that it was this one, yes. Mm-hmm. So if I understood correctly, you were assuming that the entropy stays the same as the gas phase one, is that right?
Yeah, so what we do, so actually what we've done, I did get into it, and I could send you the new paper where we actually, so the first one we did is we actually estimated the entropy. So basically we start with the phenol in the aqueous phase is literally what we're doing. And then we put the phenol into the gas phase, right? So it's like, it's now the delta G as if it's absorbing directly from the gas phase into solution and then onto the surface. So the assumption we made is that the entropy loss of that step is going from a gas phase molecule to a surface in the gas phase, like an ultra high vacuum entropy. That's the same as the gas phase phenol molecule absorbing through the solution and onto the surface. So basically the entropy of—
The reference is always the gas phase?
Yeah, the reference is still the gas phase, exactly. So recently what we did is, you can actually directly get that, is recently have a paper where you measure the delta G here as a function of temperature. So we did it at multiple temperatures. And then through that, you do a Van Hoff plot, and you can directly get the delta H and the delta S. And this is not a great, it's a little bit off there. We're actually losing less entropy than in the gas phase because you're moving this water, and the water gains a little bit of entropy itself, but it's it's an okay approximation, right? But the reason, that's what
I also think that this phenol on the surface, when it's in the gas phase, would have a lot more mobility, right? A little bit more like a 2D gas.
Yeah, I think that's so. But yeah, that is their approximation, which could be an incorrect approximation. But yeah, we're assuming that the gas phase phenol on the surface and the aqueous phase phenol on the surface are basically the same. Which is, we haven't done any simulation to show that, and that could certainly be one of the reasons we're getting some not perfect agreement between the models, right? But yeah, absolutely right. But I think the main, for the entropy, the magnitude of those changes we felt was, as a first pass, was so much smaller than these enthalpy penalties. But you're absolutely right. I think the entropy is a big portion of it. It's kind of, we're making some big approximations just because we have a reasonable ones. Yeah.
Thanks.
Great. So we have one question from Sudarshan. Great talk. So is the 200 kilojoules per mole value of the gas phase platinum estimated for the step site? If so, how do experiments in aqueous and gas phase compare for the terrace site?
Yeah, so it's actually, the 200 kilojoules per mole is for the platinum 111 terrace site. So it's like so it is the active site that we're talking there. The calorimetry values, Charlie's only done UHV calorimetry for platinum 111 single crystals. Brian has done calculations on the step sites, and I don't have the numbers off the top of my head. They're stronger. The phenol in the gas phase absorbs more strongly to, I think we did 110 and some 553 step sites, and it absorbs more strongly onto those. And then if you incorporate the bond additivity model for it, which, again, like Andy's pointing out, there's a lot, like some of these differences, I don't know if I really want to say, oh yeah, like 5 kilojoules per mole is a real difference. But since the water also absorbs more strongly to those sites, in the aqueous phase, I feel like my intuition is that in the aqueous phase, phenol is still binding stronger, or it is still binding strong. Let me see if I can go back. In the aqueous phase, the step sites are still binding stronger to the phenol stronger by like roughly 20 kilojoules per mole. The calculations are saying in the gas phase, it's a bigger difference than that, like maybe like 40 or 50 kilojoules per mole. And again, I think the difference is because on the step sites, you're displacing this water that's more strongly absorbed to the step sites than the terrace sites. I can send the exact numbers if you're curious, but that's kind of how we're understanding it, is that a lot of these big gas phase differences are a little bit smeared, a little bit lessened at least, because you have to move this solvent, which also is absorbing more strongly to certain sites than others.
Great. So we have a question by Jai. So Jai, you can unmute and ask the question.
Hi, thanks for the really great talk. I thought it was really insightful that we have to think about solvent displacement when just qualitatively thinking about adsorption. And I'm curious how general you think that this kind of intuition applies, because on the previous slide you have pulled up even for benzaldehyde adsorption on, I think, similar surfaces, it looks like the solvent effect is not as strong. And so I'm just curious, what systems do you think that we really need to consider this effect for?
Yeah, I think solvent effects in general always have to be considered. It's just when they have to be considered in the sense of, like, I guess it's like, how accurate do you want to be, right? Like, so even things like, there's a ton of work right now that people are doing for hydrogen evolution, right? So like the simplest way for hydrogen evolution, people really like, oh, just gas phase hydrogen, that describes everything. And people are showing, no, that's not the case. Like, if you really want to get it accurately, you have to incorporate, like Andy's doing a lot of this stuff as well. Like, that's not, it's an okay descriptor to kind of qualitatively do things, but if you want to get things quantitatively, so that'd be my just caveat. Like, I think solvent effects are always important. It's just a level of detail that you want to do. I think why, Yeah, I think why for phenol it's such a big deal is because it's a very large molecule. So I think a lot of these aromatics, for sure, it's going to be a significant thing. You know, and like cyclohexanol also, it's a big factor. But I think even like smaller than C6 molecules, things like ethylene and those types of things, people have done some semi-qualitative work on that, where they say, okay, you know, this is what we roughly know, and we don't really see it absorbing as strongly in the aqueous phase. So even things like that, like C2, C3s, there's a little bit of effect that's kind of lesser effect. And I think it's just proportional to, you know, how big of a footprint of what is displacing. This particular model that we've done is really for this kind of flat molecule adsorption. We feel it does apply very well. The reason for why it needs to be flat is because basically what we approximated is that the interaction between the phenol is, when we think about the solvation of the phenol in solution, it's basically from one half of the phenol interacting with water, and then the other half of phenol interacting with water. So we basically split it up into two, right in there. For more complex molecules, right, you'd have side effects and all these kinds of things, which I think would make it more difficult. But if you could get that very accurately, and you could basically, so some of these implicit models, I think if you get the cavity formation energy very accurately, it would do the same thing. But for this kind of extremely simple model that I have up here, it needs to be these flat molecules to be able to get the math very simply right. But certainly in DFT, you could, if you could calculate all these interactions, I think, in my opinion, it would be applicable to a lot of different things, but just, you know, these energies.
Thank you.
Great. We have another question by Kevin. Thanks for the interesting talk. In the case of phenol, the presence of solvent decreased the adsorption relative to gas phase. Applying this concept of adhesion energies of the solvent, what properties would the solvent have in order to increase the adsorption? Or is it only possible to decrease adsorption relative to gas phase?
That's a great question. So it is possible. So the adhesion energy inherently will always make it less favorable, just that component to it. But it depends on so again, it depends on your reference state. So if we're looking at this, if we're trying to say, like, the corresponding is this R group going onto the surface with no gas phase, in the gas phase, that's the only feature. If we're comparing it to this one, if the solvation of the organic, like, right, so basically what we're saying is at this end, this interaction between the organic and the solvent above it is basically one half of the solvation energy, right? So one half of the phenol is now solvated by water. So that's a favorable interaction, right? But in phenol, because you're moving this water, the adhesion energy is so much larger, right? The adhesion energy is larger than this kind of favorable solvation of the phenol being interacting with it. So if there was a solvent that basically did not adhere to your surface, so really, really weak adhesion, which there are a bunch of molecules that do that. And then the solvation of putting this organic group from the gas phase into the solvent is very, very favorable, then mathematically that would be a stronger, like, effective adsorption than there. So basically you need both the phenol the organic to really, really want to be in solution as opposed to in the gas phase. And then also you want the solvent to really, really not interact strongly with your metal that you're absorbing to. And mathematically, that would result in a stronger absorption. I don't, off the top of my head, know a solvent, you know, combination that do that, but I'm sure there are some.
I have a couple of questions, so maybe I'll start with the so the Faraday efficiencies. I was wondering, I'm guessing initially they might be slightly higher, but then as you go more cathartic, hydrogen evolution would start to take over. Yeah. So is that something you see? And
that's exactly right. Yeah. So I don't think I have the. Well, let me go to the plots of the chart, and I can kind of sketch out where the Faraday efficiencies are on it. But you're exactly right. So basically, what's happening when we apply the potential, we think. As you go to more and more, as you go to more and more, it's froze. Okay. When you go to more and more negative potentials, the driving force for hydrogen on the surface is more and more strong, right? So you want more and more hydrogen on the surface. So for hydrogen evolution, roughly, the rate of hydrogen evolution is going to be the amount of hydrogen on the surface squared. And for hydrogenation, it's the coverage of hydrogen to the single power. So as you go to higher and higher hydrogen coverages, the Faraday efficiency for hydrogen evolution goes up, and the Faraday efficiency for electrocatalytic hydrogenation goes down. Yeah, this is the plot, yeah. I think you guys can see this one, right? So roughly what we're saying is that the Faraday efficiency is just going, for electrocatalytic hydrogenation, it goes up a little bit and then it just decays very strongly. So you can see that there's actually this turnover here so this is the turnover frequency for phenol hydrogenation, but the current is actually going up and up because more of the current is going to hydrogen evolution. So in this kind of sweet spot, we're about 40% Faraday efficiency for electrocatalytic hydrogenation. Here, it's like 10 or less percent.
Mm.
Yeah.
Okay.
And how we believe it's happening is because of this, just the coverage effects seems to explain. There might be more complicated thing, but it's roughly described by the coverage effect. This is kind of unrelated, but I thought I'd, there's also some very interesting ones. Yeah, so these are the numbers. Phenol on platinum, 40%. I didn't talk about it at all, but we've done some work on benzaldehyde as well. And the benzaldehyde one is just kind of a strange one because for some reason on palladium, let me see if I have, yeah, for some reason on palladium, the Faraday efficiency for palladium to do benzaldehyde hydrogenation is like 100%, which it's very strange. It just stays as this palladium metal, and it's so reactive to make benzaldehyde that basically no hydrogen is going to hydrogen evolution. But that's like a special combination, the benzaldehyde palladium combination.
Yeah, I was actually reading this paper. I was also wondering myself why that would be the case, because if I looked at the DFT adsorption energies, I think that for rhodium, platinum, palladium, like the benzaldehyde adsorption energies are not very different. And so I was wondering, why is the adsorption energy, like the constant much higher for palladium than it is for platinum and rhodium?
Yeah, it's a very good question. I don't have, honestly, I don't have a good answer why it's causing this, but all we kind of know is there is this significant reason that, I mean, the two cases that it could be that benzaldehyde binds so much stronger to palladium than to the other surface that it completely covers it, and the hydrogen coverage is very low because benzaldehyde binds more strongly to palladium. Like you said, the DFT doesn't seem to support that, so that's not true. The other thing is it could be that the reactivity for benzaldehyde on palladium, for some reason, uniquely is so high compared to platinum or rhodium that just as soon as a hydrogen forms on the surface, it reacts with benzaldehyde, and you just can't get a buildup of hydrogen on the surface. The only thing we know experimentally is the hydrogen coverage when you're doing benzaldehyde hydrogenation on palladium compared to platinum benzaldehyde hydrogenation, rhodium, is the coverage on palladium of hydrogen is so much lower than the other ones that it makes sense the Faraday efficiency is high, but we don't know why in the first place it's so low, right? Yeah. And especially why the strange part is that if you do it with phenol, there's tons of hydrogen on the surface for phenol with palladium hydrogenation. So there's some unique combination of benzaldehyde and palladium that we don't see with really any of the other combinations of the metals that give this like really, really high Faraday efficiency.
Yeah, because also profs are very similar. The intrinsic activity is also very similar, right? So even that might not explain why. Yeah, I don't know. Yeah.
Yeah. So this is because like, I mean, this would be fantastic if we could find materials that could selectively hydrogenate certain things, but this was kind of, fortuitous one. And we know why it's happening in the sense of like, oh, this is what the catalyst is, but we don't know how to reproduce it with another combination of molecules, which would be fantastic if we could do that.
Okay. I just have one more quick question. I was wondering, have you or anyone else looked at some of the weaker binding metals like gold or silver for electrocatalytic hydrogenation? And I asked that because their water adsorption would be a lot weaker. And so maybe the adsorption energies in solution might eventually be very similar to platinum and palladium because you don't have that much of a penalty for the displacement of water molecules. And in addition, you might be able to suppress hydrogen evolution because those metals don't really promote hydrogen evolution. So
That's a very good question. I haven't looked at them specifically. I know that some of the groups, Udishnu, who was a postdoc at the same time, they looked at, I think, nickel, and maybe they looked at copper for benzaldehyde, recently. I don't know if anybody's looked at specifically gold and silver, other than maybe doing a CV in the terms of, but that's a great thought that some of these molecules would do there. One of the things that we thought is that for this specific mechanism, you still need to absorb the hydrogen onto the surface. So for materials that the problem with copper is that copper wasn't getting hydrogen onto the surface until more negative potentials that we were already getting some reaction for palladium platinum and rhodium. So if you're really trying to minimize the total over voltages for this, not have to go to really negative potentials, that's not beneficial. But you can basically replace platinum with copper. That has its own advantages. But that's kind of why we were keeping with these ones that are able to put hydrogen on the surface very readily. Because you can do these kind of reactions at more negative potentials on those kind of transition metals, but usually the over voltages are pretty negative compared to this. So it's really just a question of how much are you willing to give up on the electricity costs, essentially.
Great. I think we have time for one last question from Andy, and yeah, sure, you can go ahead.
Yeah, so thanks. So I just wanted to ask a bigger picture question. So I think that this area is really interesting of basically bio oil reforming. And there's this famous paper, I guess, several years ago now that claimed that if you could do all of the deoxygenation and the hydrogenation with renewable hydrogen, which this is basically a special case of, then you can basically triple the energy content of bio oils, or sort of the biomass sector, which really gets it into a competitive area where it can really start to do really big things for the economy. And so what I'm curious about is this idea of doing this electrocatalytically, and just how messy bio oil is. I used to work with bio oil as a PhD student. And we're looking at sort of model compounds here. Do you think there's a potential for this to be competitive versus doing similar reactions with just heterogeneous chemistry and hydrogen, H2?
Yeah, I think fantastic question. So the CTI, that was kind of the funding source at PNNL, this chemical trans, they looked at a lot more. They had people looking at real bio oil systems. So really all the stuff I talk about is super fundamental, very far from the actual bio oil. So of course, that's one thing. In talking to them, a lot of them that do actual treating, with thermal catalytic, is what they saw the role of electrocatalytic in that process is some of these initial streams that they get, they just can't heat up to the temperatures that you would do the normal thermal processing with hydrogen. So they thought of electrocatalytic as a precursor step to kind of stabilize these bio oil streams, add a little bit of hydrogen at low temperature, and then they figured that you might be able to, either using the hydrogen from the co-produced hydrogen, you'd use it later. But their opinion, and I don't want to speak too much because I haven't really studied real bio oil, so I don't want to go too much. This is just kind of in chats with them. Was that it might be a pre-preparation step leading to some of these incorporations with the more what you say, traditional bio oil treating systems. I think that, of course, that's specifically for bio oil. I think a lot of these electrocatalytic ones, depending on what your feedstock is, they might be able to do it purely electrocatalytically. And I think some of the fundamental chemistry, since we can apply it to a lot of these different systems, it's possible. But that's my understanding from talking to the PNNL guys on how, or the Idaho National Lab guys also, is that they thought it would be one of the steps to kind of, to get it to a final product. And they, maybe there'll be enough developments that you could do it purely electrocatalytically, but that's kind of how they saw the current state of the art as of maybe a couple of years ago.
Okay, thanks.
Okay, great. So thank you everyone for attending and for the discussion. So Nirala, did you have another Zoom link that we can?
Oh yeah. So
I will do that. Thank you.
Okay, yeah. Thank you so much. See you.